10, we're going to take a look at improper integrals. An improper integral can be one of two things. Either it's a definite integral that is on an infinite interval, so one or both of the limits of integration are infinity, or you have a discontinuous integrand. We'll take a look at examples of both of those. We know that an integral represents the area under the curve. The first technique we're going to try with improper integrals is to replace infinity with t, take the antiderivative, and then take the limit as t approaches infinity. So if you take a look at the improper integral in example 1, this integral is improper because one of its limits is infinity. This function that's pictured is 1 over x squared, and we're looking to find the area under the curve from 1 to infinity. This dashed line marks off the value 1, and so we're really calculating the shaded area in this very narrow space between the curve and the x-axis. To do that, you will replace the problematic limit with t. Now you treat this as if it was any other integral, like from 1 to 4, 1 to 5. You do it the same way as you would do in those situations. So because we're really looking at x to the negative 2 power dx, the antiderivative for that, we add 1 to the exponent and then divide by that number. And we would be evaluating this antiderivative from 1 to t. So this is the same as negative x to the negative 1 from 1 to t, which gives us negative t to the negative 1 minus negative 1 to the negative 1. The first term is really just negative 1 over t. The second term is going to become addition, and 1 to the negative 1 power is just 1 over 1, or 1. The last step then is we know what the antiderivative is. Now we want to let t approach that value that we were replacing. So in this case, it would be appropriate to take the limit as t goes to infinity of negative 1 over t plus 1. If you substitute bigger and bigger numbers in for t, what happens to this fraction as a whole? So if I have negative 1 over 2 versus negative 1 over 10 versus negative 1 over 1,000 or a million, this limit goes to 0, and then we're just left with 1. So that is the limit. And we have just shown that this integral, we didn't show that it's going to equal 1. We're going to say it converges to 1. The reason being, we're taking an integral for a shaded area that goes to infinity. So if we could actually attain infinity, then it would equal 1. But since we will just get closer and closer and closer, we say that the integral converges. Now, the next example does look very similar, but notice there's just an x in the denominator. And when we look at the picture of 1 over x, again, it's very, very similar to the picture for 1 over x squared. And once again, we're finding the shaded area from 1 to infinity. So the first thing we're going to do is notice, yes, this is an improper integral because of the infinity. And we're going to put in the t value to replace that problematic value. Same steps as before. And in this case, the integral of 1 over x is actually the natural log of x. The natural log of 1 is just 0. So we really are just left with the natural log of t. Now we're going to want to take the limit as t goes to the value it was replacing. And what happens when you put t into the natural log? So this is the graph of the natural log function, and it does seem that as the x values get bigger, the y values are also getting bigger. We can look at the table of values for this function and observe what happens there. And the question is there going to be an upper boundary, or does this function keep getting bigger, bigger, and bigger? And by putting in some values, you can see that the y values are tending to infinity also, just at a much, much smaller rate. So what we've just seen is that the limit of the natural log is going to tend to infinity, and that is what we would say our value for our integral would be. And by writing infinity here, what we're saying is this integral is never going to converge. It's not going to approach a finite value. So we say this integral diverges to infinity. So you have to be careful because even though these pictures look the same, they have very different behaviors. And this process of replacing the problematic limit with t is going to help us sort that out. In example 3, you can see this is an improper integral, and it's improper at both limits. We want to split this integral into two integrals where we only use one infinity at a time. So I'm going to have this first integral, I'm going to choose where to split it. I'm going to say go from negative infinity, and just because 0 is a nice number, I'm going to go from negative infinity to 0 of this function for my first integral. And by adding to that 0 to positive infinity, you should agree that those two integrals combined would be equal to this first single integral. Now, the reason I did that is because now I can use that approach of replacing the improper limit with t. And because we're going to work with two integrals at the same time, I'm going to be careful here and actually use two different letters. So I'm going to use t for my first integral and r for my second integral. Now, these integrals that are sitting here, again, we would just find the antiderivative in the normal way. And there was a special case here. This integral is specifically equal to the inverse tangent. So for the first integral, I'm going to have the inverse tangent of x from t to 0. And for the second integral, I'm going to have the inverse tangent of x from 0 to r. Now substitute the values using fundamental theorem of calculus. At this point, notice I have the inverse tangent of 0, and then at the end, take away that value. So these two are just going to cancel each other out, and I'm left with the negative inverse tangent of t plus the inverse tangent of r. So now I will take the limit, and for the first one, t replaced negative infinity. So I'm going to let t approach negative infinity for the inverse tangent of t. And then I'm going to add to that the limit as r goes to r replaced positive infinity, inverse tangent of r. What happens to the inverse tangent as the numbers get closer and closer to negative infinity? Here's the graph of the inverse tangent. So as x starts at 0 and heads to negative infinity, we're going to check out what the x values do. And in this case, you can see that they seem to be approaching about a negative 1.5. They're actually approaching negative pi over 2. On the right-hand side, the values, again, seem to be approaching some 1.5 value. Does turn out to be positive pi over 2. So for the first limit, and I did forget to put a negative sign in here. So for the first limit, we have negative, and then the inverse tangent of t as t went to negative infinity was negative pi over 2. And then we are adding to that, as r approached infinity, the inverse tangent went to positive pi over 2. So we really have pi over 2 plus pi over 2, which equals pi. So we would say that this integral converges to pi. In example 4, you'll notice when you glance at the limits of integration, you don't see any infinities. So why are these integrals improper? Look at the two values that you have and imagine putting them into this function. 1 over x squared has a discontinuity at x equals 0. And specifically, you can see by looking at the graph that it's an infinite discontinuity. There would be an asymptote at 0. So for that reason, this is the one we would deem the improper value. And again, that is because there is a discontinuity at x equals 0. So when you have a discontinuity, you're going to approach it the same way. You're going to replace that problematic value with t, take the antiderivative, and we've already evaluated this integral, so I'm skipping through a couple of steps here. You're going to get negative 1 plus 1 over t. Now when you take your limit, you want to let t approach the problematic value, 0, but it's very important that you approach from values inside the integral. We're really going from 0 to 1. So I only want to look at the values as they go from 1 and approach 0, which means we're approaching 0 from the right-hand side. So notice I put a little plus sign on. You always need to approach from inside the limits of your integral. So I'm taking the limit of negative 1 plus 1 over t. Now obviously at 0, if I were to just plug in 0 for t, I have an undefined fraction. So again, instead, I want to think about, what does this approach? Well, if t is getting closer and closer to 0, you can see that starting at 1 on this graph, starting at 1, and as we get closer and closer to 0, the y values are just trending upward. So this limit is infinity. Therefore, we have just shown that this integral diverges to infinity. What about the same function, but from negative 1 to 1? Negative 1 to 1 includes a discontinuity also in the middle of the integral. So this one may not look improper to you at first glance, but you need to consider if there are any discontinuities in your function. And there is one at x equals 0. In that case, you're going to want to split your integral into two integrals, where the first one ends at the discontinuity, and then add to it, picking up from that discontinuity to the other endpoint. And this integral right here is the one we just calculated in the first part of this example, and we showed that this one diverges to infinity. There is a rule that states an integral only converges if all its pieces converge. So as soon as I know that this integral diverges, then the whole integral must diverge to infinity. So to summarize what we've looked at so far, in general, when you work with the improper integrals, you want to find the improper limit, the impropriety. It could be infinity, it could be negative infinity, it might be one of the endpoints of the integral. It's wherever the discontinuity is. Then consider the limit as t tends to that troublesome value, and again, either from above or below if it turns out t is finite. And this box here is just summarizing what we talked about, that if that limit exists, your integral converges. If you find your limit doesn't exist, then it diverges. We're going to do one more example because you need to realize that not only do you need to use this new information, but you also should bring in appropriate integration techniques that we've already talked about. So this is an example not in your book. And the first thing that I want to figure out is why this one is an improper integral. It goes from 2 to 3. And if you think about substituting 3 in here, 3 take away 3 would be 0, and square root of that would also be 0. So I have a discontinuity at x equals 3. And if that isn't obvious, again, take a look at the graph and you should see it there. So in this case, this upper limit is the one that's problematic. So I'm going to begin by replacing that with t. And now I have to be able to take the antiderivative of this integral. All of the techniques that we learned are on the table here. So this could be a u substitution, integration by parts, trig, all of those things. You might think, oh, that radical, that seems like that trig substitution stuff, but notice that the x is not squared. So I'm just going to go ahead with the most basic technique and do a u substitution, letting u be the stuff under the integral. I like that option because then I get du is, the derivative of u is going to be just negative dx. And I can move that negative back over to the left. And I have a nice simple substitution for du. So in terms of matching up parts, I've got the 3 minus x here. I've got something to replace the dx with. But notice I have x, and that does not match any part of my u or my du. So, little review. In that instance, you're going to go back to your u and solve it for x. So I'm going to add x over to this side, so I have x plus u equals 3, and then I can subtract u back the other direction. And now I have something to replace x that's in terms of u. So I'm going to write the equivalent u integral. Don't forget to put the negative sign in front and then the du at the end. And now I'm going to need to rewrite that square root as a power. And because it's sitting in the denominator, I am going to use a negative exponent to bring it up out of the denominator. So I get 3 minus u was my original numerator, then times u to the negative 1/2 power du. Continuing along, I would next distribute this u to the negative 1/2, and I would get 3u to the negative 1/2 power minus, remember when the bases are the same, we're adding the exponents, so I'm going to get u to the 1/2, which is positive. And now you should be able to take your antiderivative and then replace u with x. So at this point, I found my antiderivative, and then I took the u out and replaced it with what it's equal to, which is 3 minus x. And now is the time I can put the limits back on, which is 2 to t. Now that my antiderivative is back to being x's, I can use the same limits of integration as on the x integral. And I'm going to finish by substituting those values in using fundamental theorem of calculus. If we do some simplification at the end, something nice happens, namely inside the parentheses, these both just turn into 1, and then 1/2 power is the square root of 1. So we're just really going to end up with 6 out of this first term. And out of the second term, same sort of thing happens, and we're really just left with minus 2/3. Now it's time to take the limit. So I'm just going to go in front. And what do we want to let t approach? T was taking the place of the 3, so we need to let t approach 3. And then we have to decide from which side of 3. So we're beginning at 2 and going to 3, which means we're approaching 3 from values below, which would be to the left. So therefore, you're going to see me put a little minus sign on this 3. And as you approach 3, notice what happens here. If you were to substitute 3 for t, you're going to get 0. And this is now just a positive 1/2. So the square root of 0 is 0 times 6 is 0. So this first term becomes 0. The second term also now has a positive exponent, so it will become 0 as well. So the limit, as t approaches 3 from the left, I have the negative sign in front, and then I have -6 plus 2/3. And once you're just taking the limit of the constant, the answer will be that constant. Just distribute the minus sign inside. 6 take away 2/3 is the same as 18/3 take away 2/3, giving us an answer of 16/3. So therefore, this integral has been shown to converge to 16/3. So in this example, you can see how we used u substitution to help us get to our antiderivative. All the integration techniques are on the table. So once you complete the homework assignment from this section, then you should go ahead and try Lab 5, because in Lab 5, you're going to check the results that you got from the homework.